So welcome to today's seminar. The TransferLab seminar is a platform where researchers and engineers share and discuss recent advances in AI and machine learning, striking a balance between accessibility and mathematical depth. Today, our guest and speaker is Antonio Vergari. He's an associate professor in machine learning and a member of LS unit at the University of Edinburgh. His research focuses on the efficient and reliable machine learning in the wild, tractable probabilistic modeling, and combining learning with complex reasoning. He is interested in unifying probabilistic reasoning. Recently, he has been awarded an ERC starting grant called Unreal, a unified reasoning layer for trustworthy ML. Previously, he has been a postdoc in the STAR AI lab led by G. Vandenbreck at the UCLA. And before that, he did a postdoc at the Max Planck Institute for Intelligent Systems in Tübingen, Germany, supervised by Isabel Valera. He obtained a PhD in computer science and mathematics at the University of Bari, Italy. Antonio, thanks for being here today, and we're very much looking forward to your talk.
Thank you so much. Thank you for the invitation and the opportunity. I am Antonio, and I'm going to talk about some of these recent advancements that we have in this community, the tractable probabilistic modeling and inference community. So some of these things are coming from the broader community, and some are coming from my lab. My lab is called April. We are based in Edinburgh. Here's the link here. And April is just a very flexible acronym. It describes very well some of the things we care about in the lab. So for example, we would like to model and design autonomous and provably reliable intelligent learners. Or, for what I'm going to talk about today, something about probabilities, integrals, which are these big computation beasts that we want to tame, and logic. Or in general, it's just a super fancy kind of acronym that is very flexible. But without further ado, so this is going to be at a very high level, the topic of what I'm going to describe and talk about today. How can we take some deep generative models and shaping them such that we do get flexible and reliable reasoning, both in the probabilistic sense, but also in the logic sense. But overall, in the end, whatever I'm going to show you, it's going to be a huge love letter to mixture models. This is the essence of what I'm going to talk about. Let me do one step back, however, and motivate why do we need this reasoning, probabilistic reasoning, but also logical reasoning with machine learning models. These days, we are deploying machine learning everywhere, and some of these places where we're deploying machine learning models, they come with high stakes. They are safety critical. For example, you might have like an application in the medical domain, and you may want to reason about the behavior of a model and ask it, what's the probability that whatever patient we're treating, for which we might not observe some records, the treatment is going to have a certain effect. Or, second scenario, you might have a bank deploying a machine learning classifier to make predictions about giving or not a loan to someone, right? And there you want to inquire, you want to reason if the classifier is going to be fair. And you want to make sure that it doesn't make decisions based on some predicted attributes. Or in another kind of prototypical scenario, when you have self-driving cars, we would like to certify that this machine learning system we deploy are not susceptible, they cannot be attacked by adversarial examples. How do we answer all these queries, all these questions about the behavior of machine learning models? Well, we need to formalize them. And one way we do this is to use the language of probabilities. So we take those questions and we translate them into formulas, mathematical formulas that we want to compute. And some of these formulas involve big integrals of big expectations, right? And this is going to be a recurring theme of my talk. How do we deal with these big integrals and big expectations here? For example, for whenever we have missing records of the patients, we might want to treat them as missing values. So we just want to marginalize them out. That would be the probabilistic way to deal with this inference problem. When we have the fairness scenario, we have lots of fairness metrics. One of these is reported here, is the difference of two expectations, where the expectation is taken with respect to some sensitive attribute, okay? And that's essentially saying, no matter which value of these attributes I see, I don't want the behavior of my regressor or classifier to change in expectation. Lastly, for the adversarial robustness, very clever people have come up with a way to certify that your classifier as it's never going to change its prediction based on adversarial attacks. You can do this if you're able to compute exactly this other expectation here. So these are the big expectations and integrals we want to compute after we translate our reasoning task into the language of probabilities. There are many more other scenarios. These quantities appear everywhere if you want to do probabilistic programming, computing uncertainty in a Bayesian scenario, or neurosymbolic AI. Later, I'm going to briefly touch the neurosymbolic AI scenario. But for now, let's do one step back and let me elaborate a little bit more. Why these quantities are tricky? Well, because in general, we don't know how to compute integrals in closed form, or when we know, the complexity of doing that is sharply hard, or NPR. It's something that's very hard computationally speaking. So the question is, can we find a kind of middle ground and design some models that lets us compute these quantities efficiently and reliably? I want to compute them exactly because if I use these quantities to peek into the reasoning behavior of machine learning models, and I want to certify robustness or understand if a model is fair or not, I don't want to pile up additional error. I want to compute these quantities exactly and have a clear answer if the model is fair or not, robust or not, and things like that. And then I want to do this efficiently. So in computer science, efficiency sometimes is just said polytime, but polytime is kind of like a big umbrella. For most of my talk, polytime essentially is just going to be linear in the size of my computational graph. So imagine you have a computational graph, a neural network, and we just do a single feed-forward pass, and we compute these quantities exactly. If I put these two ingredients together, exactness and polynomial time computation, then we get tractability. So this is the nutshell, the core definition of tractability for probabilistic inference when we want to reason about machine learning models. Why do we need this tractability? Well, in many scenarios, I really want to compute things exactly. So I don't want to have errors, or want to have like the best estimate of my error to bound by error because the estimate is 0. Some other times I want guarantees that the behavior of my model is conforming to what I expect it to do. I might have constraints, for example, having a robot that needs to follow a path, and I really want the robot to stick to the path. I don't want to make a prediction that is not a path or the robot to go on some terrain that go outside the path. So that's why exactness comes into play. And then efficiency comes into play because many times when we have models that are intractable, well, they are much slower than models that are tractable. So even if we think that models that are intractable can be more expressive, in practice, if we want to perform inference over them, then we might take quite some time. For example, this plot is taken from a paper we did when we wanted to compute the expectation for the adversarial robustness. And here we have a model that can compute that in closed form exactly. And that's quite efficient. Only takes like fractions of seconds to do that when the model size increases. If you want to do that with Monte Carlo and approximate the expectation instead, to get a level of confidence that's not 100%, but it's 99.99, you need to get millions of samples. And this is going to be extremely slow, even if you parallelize on the GPU. On the other hand, if you want to compress your data, there is super nice work by Angie and colleagues, where they use a probabilistic circuit, one of these models I'm going to introduce in a bit, that gives you an extreme fast decoding time and encoding time to compress and decompress your data while being equivalently accurate or maybe even more accurate than other intractable models that are based on normalizing flows, variational autoencoders, and things like that. So here's my goal. I want to find some kind of middle ground for a representation that lets me balance tractability and expressiveness. And I'm going to show you, I'm going to approach the problem by sketching this cartoon. On this y-axis here, I'm going to rank models, putting them on the top if they are more tractable, meaning that they support more scenarios when they can compute more quantities exactly and efficiently. And on the x-axis instead, I'm going to put models on the left. They are more expressive in the sense that they can represent more functions with the same budget of parameters. And then the cartoon goes in this way. Many deep generative models, like diffusion models, normalizing flows, VAEs, GANs, and so forth, they definitely are expressive, but not tractable. We need to come up with approximations. They don't come with guarantees and therefore we might not be using them reliably for the purposes I just showed you before. Other simple models coming from your textbook of probabilistic graphical models, for example, like HMMs or trees or Gaussian mixture models, definitely are more tractable, but they're also inherently simpler. So they are also less expressive. You have less parameters to tune. Between this spectrum here, there is like a Pareto frontier. I don't know if you can see my mouse here, but I would like to navigate this frontier and then possibly be in this orthont. This is where this framework of circuits, which I'm about to introduce, are going to stay here. But more importantly than being here, it's how do we get there? Okay, how can we be both expressive and tractable? And the idea is this: if you have a simple model that gets you tractability because it has structure, but not many parameters, then you can over-parameterize it, bring in more and more parameters, and then keeping the structure, you return the tractability. Or if you start from an intractable model that is quite over-parameterized, has lots of like knobs to tune when you learn it, then you impose a little bit more structure. These are kind of the recipes we use in the circuit community to get like a good balance between tractability and expressiveness. How do we design these models that are going to be computational graphs that will be expressive, but they also efficiently encode inference? All these big operations, big summations, big integrals, big expectations we want to solve. Well, here's the framework of circuits. The idea is simple. In a recursive way, we're going to build these computational graphs. And the trick is, you're not allowed to put whatever you want in your computational graph, let's say in PyTorch or in JAX, but you just have a bunch of ingredients and 3 simple rules. The first rule says you can have some simple units, they encode simple functions. For example, a simple density, and therefore you can have a Gaussian distribution, or a simple mass, and so you can have a categorical distribution. Just simple unit that outputs the density or the mass of your random variables. Or you can mix them into the sum. That's our second rule. We put a sum unit here that weights the outputs of some other previous units you have in your computational graph. And this is the sum unit. From a probabilistic point of view, it realizes a mixture model. And this is why mixtures are going to be all over in this talk. Rule number 3, and last rule, we can also combine sub-circuits by doing their products. If you do the product, as you will see later, we will assume somehow some structure here that will essentially encode a factorization. So locally, we will assume that the 2 sub-circuits will be independent, but just locally. Then we can mix them together, like in this scenario, and then they become, again, by introducing more parameter, more expressive, because here we have a mixture model over something that decomposes. But this, we are not just limited to just putting a sum over some products. We can go deeper and just reduce the same idea of deep learning, building a model that is stacking together many sums, many products, many sums, many products, one on top of another. And every sum comes with some parameters. Every input distribution comes with some parameters, and we want to train them. So this is the general recipe of the circuits, putting together sum and products, and so forth. How do we use them to perform inference? As I said before, they just are special cases of neural networks. They're just simplified neural networks. In this scenario, you want to compute the joint probability distribution over 4 variables, x1, x2, x3, and x4. And here you have a circuit that's actually defined over x1, x2, x3, x4. And for every variable, I have 2 input distributions. Think about 2 Gaussians that you are mixing in some way. The structure is given, the parameters are given, and to compute this quantity, I just need to do a feed-forward evaluation. So I feed these values that I observe into the input units. And I read out, for example, the PDF of my Gaussians, if my input units were modeling Gaussians. Otherwise, I'm going to read out whatever they're modeling. And then I keep on propagating these small values and doing sum and products and things like that, such that at the end of the circuit, I collect its output, and that's exactly going to be the value of my probabilistic query, of my reasoning step, computing the joint probability or the joint density for 4 variables. Just a feed-forward evaluation of my computational graph, nothing super fancy. So this is how we evaluate the circuit. But then I wanted to give you like 3 motivations for why circuits are a very good choice these days, and that's something that someone should have in their probabilistic toolkit. I really believe that. Reason number one, there are many models in our textbooks, and many seem to do different things. HMMs, trees, decision trees like XGBoost, even tensor networks, and other simple PGMs. With circuits, you can have a single formalism to represent many of them. And this implies that you can translate these different formalisms into the single one, reuse the same machinery, and you do not have to reinvent the wheel. Also, it's very useful to draw connections among different model classes. This is, for example, what we did very recently. We draw a formal connection between tensor factorizations, which are super popular in machine learning, especially these days when you use them to accelerate large language models, and circuits. The bottom line is that you can take a tensor factorization, for example, a Tucker factorization, if you know what a Tucker factorization is, and then translate that one-to-one to a circuit. So tensor factorizations are a special kind of circuit. But once I do this translation, then I can reuse whatever the theory and whatever the modeling strategies I know about circuits without having to deal with the specific syntax or the nuances coming from the formalization of tensor factorizations. This holds for tensor factorizations, but also for other model classes like HMMs, trees, and so on and so forth. Why am I really interested in the tensor factorizations? As I said, because they are very well understood and used, largely used in the machine learning community, but also because the way we learn circuits these days is essentially building and stacking tensors together. And this goes under the dimension of overparametrization, as I was telling you a couple minutes before. How do we do this? We start from a kind of a template for how to split our variables. It might not be clear why we're doing this now, but it will be clear in 10 or 20 slides, which are actually most animations, so no worries. And the reason is that we want the structure. As I was saying before, we keep some structure on the way the circuit should behave. This is a template. It's like a recipe we call the region graph. We split variables somehow. And then, for all the possible ways in which we split these variables, we start over-parameterizing the circuit, which means we put a certain number of units in every bucket, in every layer, and we connect them such that we have some locally dense tensor here. There are many ways to do this, and actually these are choices that can be picked up by users or discovered by a machine. And essentially we have abstractions for these layer types. I don't have time to go into details, but I can point you to some references in the literature if you're interested. Then we select how many units we want for every layer. As I said, that's also an hyperparameter. How many input units here, how many sum units for the layers, so on and so forth. And then we have ways to connect it. And every densely connected layer, it's gonna be parameterized by some parameters that we can learn. And we can just learn this by doing SGD or any optimizer that you really want to pick from your PyTorch library. Okay, you want to use AdamW, that's it. If you want to do the newest, fancier, schedule-free version of AdamW, you can just use that because all these architectures are differentiable. We are preparing a library. It should have been ready by today by the talk, but it's going to take us at least 1 or 2 more weeks. It's going to provide many of the routines to learn and reason with circuits that I'm actually showing here in the talk. If you're interested, and if you cannot wait like, I don't know, 2 weeks, then I can give you also access to that if you think like it's worth it. Back to my motivations. I said I'm going to give you 3 motivations. The first one is that you have one grammar to rule them all, to rule all tractable models, or almost all of them. The second one is that since you can over-parameterize them a lot and train everything just by SGD, these days we have large GPUs, we can fit like quite large models, and it turns out that our large circuits are pretty much competitive with intractable models, variational autoencoders and normalizing flows, for example. This is because a circuit, since we're stacking many sum units altogether, it's a big hierarchical mixture model. Or you can also think about that as being like a very, very sophisticated polynomial. But how expressive are they? These are just like results from some simple variants of images. But the best circuits we have these days, they are very competitive with respect to normalizing flows and other variants of variational encoders or the models doing neural compression schemes. This is a result reported in a paper that just got accepted yesterday at NeurIPS as a spotlight. But if you are interested in this kind of comparison, I can point you to all the different, a little bit fragmented literature of circuits and show that many scenarios, not just images, they really are competitive with flows and MVAs. And as I said before, we are really able to scale the circuits up to billions of parameters and even more these days. So we know how to do this. It's possible. But if you ask me, it's not really the fact that they are expressive that makes the circuits shine. I do prefer the first one, having a single formalism to represent many probabilistic models. But actually, the best one is the reason number 3. If you give me a circuit, this computational graph made only by sums and products and simple input units, then the way it's structured, what we call the structural properties it has, it's a contract for the tractability of the computation of some probabilistic queries or scenarios you care about. That's the beautiful part of circuits. You want to compute marginals, we know which structural properties you need to have. You want to compute expectations, you need a certain set of structural properties. You want to compute maximum a posteriori inference, the same. So I'm going to just briefly touch which are the structural properties right now. If you want to have a better view, I can point you to pieces of the literature. Here are the 4, I would say, most important structural properties we have in circuits. They have weird names, I do agree with what you're probably thinking. Smoothness, decomposability, determinism, and compatibility. You can forget about the names, abstract into property A, B, C, and D. It's not really important for the sake of this presentation you get like all the names correctly. I'm just going to give you like a sense of what's going on here. For example, if you have property A and property B, then you can guarantee that no matter which subset of your variables you pick, you can marginalize the remaining set of variables out by computing a big integral or a big sum if these variables you're marginalizing are discrete. And if you want to do that in a single feed-forward evaluation of your network, these are sufficient and necessary conditions. So that's quite a powerful thing, a remarkable property that you don't find in other probabilistic models. What are these properties? One is called smoothness, the other decomposability. But I think like it's not super important to go into the details. Smoothness, I'm just gonna say, it's a natural property of mixture models. For every sum, you just are putting in the sum functions that have the same set of variables. And decomposability is a property of the products. As I said before, you just want that the input functions of this product are defined over disjoint set of variables, such that you encode local factorizations. You can let these properties sink in a bit, or you can just forget about that and trust me that you just need property A and property B for this. Back to my example, as before, how do I marginalize? For example, if I want to marginalize out x2 and x3, I just compute the density over x1 and x4. Well, and as I promised, you can do this in a single feed-forward evaluation of your network. First of all, you just marginalize x2 and x3 by marginalizing over the input units. As I was assuming them to be Gaussians, then they're going to be normalized densities, and they're going to just output 1. For the remaining, I'm just going to feed the input that I observe here. And I'm just going to propagate as before, computing sum and products. The result is essentially the marginal, the exact marginal I wanted to compute. And what do you do when you get marginalization? If you have some image data, what you can do is try to deal with missing values, in this case, missing pixels, perhaps even sampling conditionally from this. These are images taken from a paper that now it's like 4 years old. It's okay, but the literature has progressed quite a lot. For example, there's been this super nice work presented by the UCLA team at iClear this year that is bringing this kind of idea to the next level and combining circuits with diffusion models. Now the task is in painting. So you're given a piece of the image, and then you want to sample, for example, to in paint to reconstruct what's left, okay? Diffusion models are pretty good at this, but they can also be slow sometimes. So you can hybridize them with circuits, and since conditioning and computing these marginals with circuits is extremely easy, this is where the tractable inference is going to shine and is going to help you. So here's a reference for you if you want to check this nice work. But more in general, if I just don't want to marginalize things out, but I want to compute expectations. Like in the case for my fairness scenario, I do have to solve an integral where I have two functions, my distribution P and the functions for which I take the expectation, my function F. How do I deal with that? We can do something and compute this big integral in a closed form if we represent both P and F as circuits, but they need to have like some structure. Structure is the key of tractability. So with this in mind, what are the structural properties that we need to compute, for example, the fairness query that I showed from the very beginning? This is property number 3. It's called compatibility. Compatibility essentially tells me that if I have two circuits, let's say one computes the probability distribution P, the other computes the function F I'm going to take the expectation of, whenever they have a sum, and the sum is a function over product, and the product is a function over these variables, the product decomposes, splits the variables in the very same order. And this is where having this contract, this recipe, which we call region graph, when we build a circuit, really helps. Because you know in advance that your circuit is going to be made up of product units that are always going to split the variables in the same way. If you have this compatibility, then what you can do is that you can compute its expectation in time that is worst case given by the size of the first circuit times the size of the second circuit. This is a kind of like very loose upper bound, but we know that we can do this quite efficiently these days. And as a matter of fact, I'm going to show you some applications for this, because doing the product of these circuits and then normalizing them, it's a core operation. One scenario where this really helps is in neurosymbolic AI, for example, in semantic probabilistic layers. You have some products among two circuits, and you want to enforce the reliability of your neural network. And when I say reliability, essentially saying that the neural network is going to output something, and this something must satisfy some logical constraint. And you want the constraint to be satisfied 100% of the time. This is crucial in some safety critical applications. I mentioned before some pathfinding, for example. Imagine that you have some picture, and then you want to go from this corner to this other corner. And whenever you cross over the mountain or the sand or the wood, you pay a price. So in a sense, you want to find the shortest path based on the cost you can pay here, right? The input of your neural network is this X. It's going to be this image, a simple tile map in this case. And then we want to find the best configuration of all possible labels of edges in a grid. So here, one edge is set to 1 whenever it's visible, otherwise it's set to 0. I just want to do the argmax of the conditional probability of all my labels given the input image X. But I have a constraint. And with this weird notation, I'm saying that all the labels predicted by the neural net should satisfy the constraint, which in this case means like that this configuration should form a valid path. And this should be the valid path I care about. This is a huge space, but if you impose the constraint, you reduce the space state by a lot. So that's going to be the trick. Can I impose this constraint into a neural network? Of course, we want to generalize this notion and not just deal with this path scenario, but having, for example, hierarchies over your labels. Imagine that you need to predict many labels and you're in a multi-label scenario, but you also have a hierarchy, a logical hierarchy over your labels. For example, you know that whenever you observe a cat in your input, then also the label for animals should be true, because animal is a superclass of cat. And same goes for dog. So I want to satisfy this constraint and make sure that all the predictions of my neural network satisfy this constraint. Or more generally, you can also predict not only hierarchies and paths, but rankings. So how do I make sure that the ranking predicted by the neural net is a real ranking, and it's not just a bunch of numbers that are repeated or they are shared across users? The recipe at a very high level, it's quite simple and straightforward. It says, if you take any neural network that outputs many binary variables and you remove the last layer, then you can replace that with a layer that uses the product of circuits. And this is what we call a semantic probabilistic layer. Here it's the high-level overview. So Z, it's the embedding that comes from the previous layer of the neural network. And this is mapped to some distribution Q. This Q is a circuit. This is going to be a circuit. And this is a very expressive distribution of real labels. I'm simply saying that my neural network, through this function here, computes the weights of my circuit. And then I'm going to multiply the circuit with another circuit that encodes my logical constraint. This other circuit is only going to output 1 if my output of the neural net satisfies the constraint, and 0 otherwise. A very simple idea. Basically, I'm going to put to 0 all the probabilities of the label configurations that do not make sense, that violate the constraint. Per se, this kind of computation is very well known in machine learning. It's called the product of experts, but it's intractable in general. You cannot really renormalize it. And you want to renormalize it because you want to train this layer normally just by gradient descent, by doing the classical maximum likelihood we always do in machine learning. We cannot do that in general. But if these two are circuits and they are compatible in the sense that they always split products in the same way, then we can do that. We can compute the Z and renormalize it and train everything end to end and always make sure that the output of the neural network satisfies this constraint. As I said before, the machinery is the same. We know how to do this product. We need the additional structural properties. And if we have the structural properties, we can guarantee that the computation is going to be exact and is going to run, in worst case, in times that is proportional to the size of Q times the size of C. And these are my two circuits. This is one possible recipe, but these kind of ideas are repeated over and over in the literature. So for example, when we want to use this to encode constraints when you have a knowledge graph embedding model that you can represent as a circuit again, or when you want to steer the generation of a large language model, and your constraint might be some logical formula that says what you're going to generate next should contain this token, or this other token, and later on, this combination of tokens. And then you can enforce that no matter what, the LLM is going to generate something that satisfies the constraint. Or, slightly different from these scenarios, whenever you have an agent and you want to train that in reinforcement learning, and you want to make sure that the agent only picks safe actions, actions that should be encoded in your constraint, then you can reuse the same concepts here and do the product of these two circuits. Lastly, you can also do the same machinery and tricks if you want to improve the logical consistency of LLMs, which are notoriously poor at being consistent even with themselves, not just with an external knowledge base. But so far, I just talked about mixtures, okay? So I will dig deeper into what are the limitations of these mixture models. A very general idea of mixtures in the literature is the following one. Whenever you have a super simple distribution that is tractable but not that much expressive, then if you combine that in a mixture model in this way here, you're going to get the distribution that is more expressive. If you go from a Gaussian to a Gaussian mixture model, you can model something that is multimodal. You get expressiveness in this scenario. And this is so used at, I can make it like a prediction. If you find tomorrow at the conference that a paper uses a probabilistic model A, maybe not so much time will pass after someone else, or perhaps the same team, will publish a paper talking about mixture of A. Mixtures are such a powerful idea. They have been used all the times, and we use that also when we use circuits. It's just the natural evolution of this idea. Instead of just putting in a simple sum together some components, we encode in a single computational graph an exponential number of components. We just do that very cleverly because we stack some layers on top of another, and putting intermediate product layers, essentially we have an exponential number of components that share many parameters. It's very good. It's the result of parameter sharing. That's the recipe for doing that. However, even if you're able to do this, there is some issue here. And the issue is in the very simple definition of mixture models we read from textbooks. We put together in a convex combination some components that are non-negative. And when I say convex combination, I mean that all the weights of my mixture should be non-negative, and they should be summing to 1. The fact that they sum to 1 is not super important because we can always renormalize them such that they sum to 1. But it's crucial that they are non-negative. But that, of course, means that I can only add components. And this can be wasteful. Here's the intuition why. If you have a simple density, like this donut in 2D, and you want to fit a Gaussian mixture model, to do that, and you start from only 2 components with your GMM, you're not going to do a great job. You need to increase the number of components by a lot, and you're going to need to place these components across here, right? It seems a little bit wasteful. While ideally, why can't we just put a single Gaussian here and then subtract 1 Gaussian from the middle? If you allow the weights to be negative, then it seems like we need just 2 components, k equal to 2 sets of parameters to train. So this is the idea behind subtractive mixture models, the models that I'm going to talk about in a bit, in a work led by my student Lorenzo and presented at Clear this year. I'm going to give you the theoretical result first to convince you that this subtraction really helps. The story goes in this way. Shallow mixture models with negative parameters, and I mean like shallow, not deep, only 1 layer, can be exponentially more compact, and it means very, very small to represent some distributions that cannot be represented compactly by even a deep mixture model, which means a circuit with many, many layers that only has positive parameters. The bottom line is we just need mixtures with negative parameters, and then this increases dramatically the expressiveness of these models. How does it work? The issue is that if we put like these weights here that are non-negative, and we allow them to be null R, we have a circuit what we call non-monotonic, okay? The fact that the circuit is non-monotonic per se here implies that the output can also be negative, but we want to model a distribution, so we need to make sure that the output is non-negative, is positive. We do that by squaring the circuit. Squaring the circuit ensures that the negative outputs are there, but also allows you, once we unroll the square, to have a mixture model that where we share parameters here. So we just have the same number of parameters, 3, W1, W2, W3, and these combinations can be negative. So we have 3 ways, 3 opportunities to subtract densities or subtract mass. And this is going to make the model more expressive. This is the intuition for a single small circuit. But how do we do that for a circuit that is deep, that has many layers? How do we square it and therefore renormalize it later? I told you the recipe already a couple of minutes ago. If I can do the product between 2 circuits, as long as they are compatible, there should be a way to do the square, which is the product of a circuit by itself. And in fact, this is what we do. So we take the circuit, we square it, and basically, if the circuit has this nice property that is compatible with itself, something that we call structure decomposability in our lingo, we just square every layer in the circuit. And this can be done very efficiently. That's how we square circuits. And now we can allow all the weights inside to be negative. The output of the circuits is just going to be positive. If we do that, then we can show empirically that the squared circuit, where you have both positive and negative parameters, the negative parameter is important, it's going to be much better than if you have a circuit with just positive parameters. But these days, we are going a little bit further. So in some recent work from my lab, always by my student Lorenzo, we have tried to understand what happens if we have not just a single square, but many squares, and we sum them together. This is what we call sum of squares circuit, or SOS circuits. And then we proved theoretically that if this is the class of all the functions you can represent compactly with a fixed budget of parameters that is polynomial, that's small. And then you can do for a circuit that is a square circuit with positive and negative parameters, if you allow for the sum of the squares, then you can do more. So there is some theory here in the paper, but there are also nice experiments that tell you that all these sum of squared circuits, they can be better than just like squares or just circuits with positive parameters. There are also some interesting connections because you can understand that if you use circuits with complex parameters here, essentially you're just doing a sum of two squared circuits that use real parameters. And just by using complex parameters, therefore, you're implementing one of these SOS circuits, and you're going to do better. You can do even better on standard benchmark if you multiply this complex square circuit with another circuit with just positive parameters. And this is because implicitly you're summing over an exponential number of parameters, essentially having this exponential mixture model. I think I'm reaching the conclusion. Just a reminder that the library is going to be out there in a couple of weeks, perhaps. Send me an email if you're interested.